Hello everyone, my name is Akshay Hinduja and I'm going to present our work, Acoustic Localization and Communication using a MEMS microphone for low cost and low power bio-inspired underwater robots. Commercially available AUVs are well suited for the inspection of artificial structures, surveying, and bathymetry. Many of them can do these tasks autonomously. However, they are not good for tasks which require them to be close to marine life. Bio-inspired robots, on the other hand, are great for biomonitoring and inspection of coral reefs due to their small form factor. Over the years, these bio-inspired robots have improved tremendously when it comes to control and locomotion, but overall autonomous behavior has a way to go. The ability of a robot to know its position is a fundamental need to be truly autonomous. This information is useful to tag geomonitor data and to provide relative positional commands. Underwater robot localization has been studied in detail for many years, and the most popular methods can be grouped as follows. Inertial navigation methods make use of onboard sensors like Doppler-velocity logs and IMU to perform dead reckoning. The addition of sonars and cameras allow for feature-based methods which can correct for drift over time. The drawback here is that these sensors are bulky and expensive. Other well-researched options are the acoustic methods, which require onboard and offboard equipment to function. The traditional methods are two-way travel time, which include the long, short, and ultra-short baseline methods. They require a transceiver and transponder module on both sides to determine the time of arrival to estimate position. This is difficult for a small bio-inspired robot to use because the weight and power consumption of the transponder. Ripkema and his co-authors showed their one-way travel time method, which could work with a single speaker and an IUSBL array on the robot to perform localization. The drawback for our use case is that keeping accurate time difference of arrival, which was made possible through an initial time sync with atomic clocks, and these clocks are very expensive and would make a multi-robot framework exorbitant. Thus, for smaller bio-inspired robots, what we are looking for involves it to be cheap, onboard, low-powered, lightweight, and able to localize multiple robots together. Acoustic pseudoranging is a method which would tick all these checkboxes. Inspired from GPS dilatation methods, it is a passive method on the receiver side. That means a receiver's only task is to listen for the signal. The setup costs are cheap and can be easily expanded to larger areas. Mainly, we can use ultra-cheap MEMS microphones to do this task, and no accurate time sync will be required apart from the initial sync over NTP. This is a brief overview of the optimization which takes place to estimate the robot position. Given a minimum of 4 known speaker positions, we can compute the pseudo range between each speaker and the robot, which includes an estimated time bias term. By applying a first-order Taylor expansion, we get a system of linearized equations, which on simplifying can be solved as a least squares problem. Thus, A is a design matrix, B is a prediction error, and X is the update in position and time bias. This update is used to estimate the position of the robot as well as correct for drift in the time sync using the delta dt term. As in the case of GPS satellites, finding a reliable position estimate is dependent on the speaker position geometry. A popular metric used is a geometric dilution of precision, which can be obtained using the design matrix and the covariance derived from it. A lower GDOF value would indicate a more favorable speaker constellation geometry. Based on GPS literature, it's shown a value of 0 to 5 gives excellent, 5 to 10 moderate, and 10 to 20 fair estimates of position. Beyond that, the estimates are unreliable. Our implementation of acoustic pseudoranging for bio-inspired fish is as shown. We have a central computer connected to a USB sound card and 4 speakers in known positions. A periodic sequence of 4 identical chirps are sent, which are recorded by a MEMS microphone, which expects these signals at roughly the same time period. Using match filtering, the relative time difference of arrival between the receiver and each speaker is calculated, which is used to estimate the position. We can also send an independent chirp for one-way communication with the robot to, say, perhaps perform dive or surface actions. As for a hardware and setup, on the transmitter side, we have a Raspberry Pi 4, the USB sound card, and 4 underwater speakers placed in known positions, placed in a cylindrical tank as shown over here. On the receiver side, we use a Raspberry Pi Zero W with a MEMS I2S microphone and a MOSFET trigger switches for fin actuation for the fish robot. Before our experiments, we first determine the suitability of speaker placement through a geometric dilution of precision analysis. This gives us insight on whether our position choices are good or not, and perform experiments in a water tank. The graphical results for the three configurations are as shown here. A higher covariance in Z is observed as the variance in Z position of the speakers is limited to 1.5 meters, whereas X and Y speaker position variance can be 7 meters. The mean error over the three configurations is 0.345 meters with a standard deviation of 0.228 meters. We also verify fin actuation based on the independent signals sent after the sequence used for localization. In conclusion, we show an application of acoustic pseudoranging for the onboard localization of small bio-inspired robotic fish, which is a cheap and effective way to localize multiple robots simultaneously. Small spaces like the water tank are inherently prone to some issues. Applying this framework in open water situations is likely to yield better results. Using MEMS pressure sensors and IMUs can help improve state estimates when coupled with filtering methods. Thank you for your attention. Hardware Notes and Code is open sourced and can be found on the following link and QR code. We hope this can help fast track further development in the field. I'm happy to take any questions.